Right, now let's do a voiceover for question 8. So for question 8, what we're going to do is something highly illegal. We're going to use Maclaurin's brackets. So inform your reader, the marker, that you're using Maclaurin's brackets and what they're going to look like. So tell them that they look like triangles, like here. The first thing we're going to need to do is to find the reaction values at A and C. Because we're using Maclaurin's brackets, we can in effect combine solutions for B and C together. So let's start off with A. So for that, I'm going to sum up moments, and I'm going to take moments around A. I'll go clockwise because I've got a clockwise moment being applied. And so that means that my M that I see in the graph will just be M when I sum them up. And then when I take moments around A, that will get rid of my moments turning moment A, but I create one at C. C will be going in the opposite sense, so we'll have a minus C times by L, because L is the distance away from A. And so rearrange this, and that'll tell me what the reaction is at C, and that's going to be a positive M divided by L. The next thing I'll do is I'll take moments at B, but I'll make sure that I go clockwise so that my M stays as a positive M. So M equals 0. I'll take moments at C, but I go around in a clockwise sense. So I'll draw that on the diagram so that I know which way I'm going. And I can see, taking that clock face, that the A is going upwards, so the reaction RA will be a positive moment. So RA times by its distance away from C, which is L, will be a positive moment. And then we've got a clockwise moment on the beam, so that would be RAL plus M equals 0. We'll rearrange this and we'll find that the reaction at A will be a minus ML. So why have I chosen to take moments? Because I want to use my final sum the forces in the y direction as a means to check, and this should be help me get a firm basis to build the rest of the question on. If I get the reactions wrong at the very beginning, it could be disastrous. So let's check whether this solution appears to be correct. We'll sum up our forces in the y direction, and we've got ML take away ML equals 0, so it seems to work. So that seems to be a good basis to carry on. Now, because we're going to use Maclaurin's brackets, this means we can in effect solve B and C together in one combined solution. So what we're doing here, well, the Maclaurin's brackets principle is that you're going to be cutting through the beam just as if you were doing, if you recall, in your stress level 1 notes, where you cut through the beam and you take a pivot around that particular point where you've made the cut through. But with Maclaurin's brackets, you only take one cut, and the cut is right at the end, just left of the support. So that's going to be our M. What we're doing is we're looking for summing up the moments that we can see left of us. So this, if you like, is an M function of X. Okay. So now let's look left of this cut and see what we've got. First thing that you can see is that we've got this force associated at the pivot A. Well, okay, so I ignore that. So the first thing I write down is the fact that I've got an M left of me. Okay, so I'm going to write the M, then I'm going to open up a Maclaurin's bracket, and I'm going to tell you that I'm associating that with a X distance away from the leftmost point, take away 2/3 L. I close my bracket, and then I raise that to the power 0, because first of all, notice that we've got an m term here, so we can't be timesing m's by distances. That dimensionally doesn't make sense. So that sounds a bit odd. Why am I taking m and multiplying it by a term and raising it to the power 0? Well, how this is working, it's working as a switch. So the Maclaurin's bracket tells me is that if that thing inside the bracket is less than 0, it switches off. It's a 0. And if that thing inside the bracket is greater than 1, is greater than 0, it switches on. That's when it's raised to the power 0. So that's all it does, raised to the power 0. So the other moment you're going to get is from the support at pivot A, and that's simply going to be RA times X. We know what RA is, so let's substitute that in. So we can say that the m as a function of X equals minus m, which is the value of your turning moment, divided by L times by X, plus m multiplied by this Maclaurin bracket term here. Now, let's examine this a bit further and see what this looks like if we were going to plot it out. So, as I said before, if x is less than 2/3, this bracket tells me that that term switches off. It becomes 0. So you get m times 0. So left of where the turning moment is being applied, we're simply going to get minus m divided by L times by X, and that will be true up to the point when X equals 2/3 L. So what you can do is set X equals to 2/3 L, and what we're going to get, we end up with minus 2/3 M. When we go to X, set, we have a value just a little bit left of the 2/3 L, that will switch on this bracket, and so that means that we're going to suddenly start adding M to our equation. So that means we're going to shoot up plus m on. So if I plus m to 2 minus 2/3 m, I'm going to end up with 1/3 m. Finally, how is this equation going to finish up? Well, we can substitute in x equals L and see what we get. So substitute in x equals L to the first term, you can see I'm going to get minus m. Substitute x equals L to the second term, and I can see that I'm going to get, well, that tells me I'm just going to switch it on. So I'm going to end up with minus m plus m when x equals L. So it drops down to 0. So this is what my turning moment equation is going to look like. So I've also given you a little graph to show you what it looks like. Now let's go on to the next part, part D. So in part D, we've been told to find what the equation of slope is. So you can look this, although we don't actually have this on our formula sheet, we've got a very similar term, but we're going to start off with saying that the deflection, which will be we're called y, is a second order derivative times by Young's modulus, the cross-section area of the beam, and that equals the function of m that we're going to be integrating. If you go and look on your formula sheet, you're going to see that there's an integral version of this equation where it's been integrated twice, and it's got two terms associated with it, C1 and C2, when you've integrated. So this is what we got on our formula sheet. You see, it doesn't quite do the thing we want, but you can see that if you differentiate that once, differentiate that twice, your C1 will go, your C2 will go, then your C1 will go, and you'll end up with the expression that I'm showing here. And so what we can say is that on the right hand side, this is going to be m as a function of x equals this second order partial differentiation. So I know what the m as a function of x equals. I found that previously from my part B and C, and I can simply put that in on the right hand side. So I can say I've got that this is going to be minus m over L times by x plus m Maclaurin's left hand bracket x, take away 2/3, let's try and fit in my L there, 2/3 L, close bracket, and raised to the power 0. That's so weird. Now part D wants to tell us what the equation of slope is, so we're going to need to integrate this so that we get the equation of slope. So the first order derivative is equation of slope. It's a gradient. Gradient means slope. So let's integrate our terms here. So we're going to integrate the x. That simply becomes x squared divided by 2. Now what we need to do is integrate the Maclaurin's bracket and keep everything you got inside the Maclaurin's bracket must stay there. So this is being raised to the power 0. So if I integrate something to the power 0, what am I going to get? Well, I argue that I'm going to get to the power 1. So I've got my m, left hand Maclaurin's bracket, x, take away 2/3 L, close my Maclaurin's bracket, and it's going to come to the power 1. Have you noticed I have forgotten to add something on at the end? Don't worry, I remember to do it later. Let's move on to part E. So part E, it says, now can you tell me the deflection? So this is saying, can you tell me what the y is? So I need to integrate this equation again. So on the left hand side, first order derivative, need to integrate it, that's straightforward. Now let's integrate the terms on the right hand side. So I've got x to the power 3. Sorry, I've got x to the squared, that becomes x to the power 3, divided by 3, so my 2 becomes a 6, 2 times 3 is 6, and now let's integrate this term here. So you've got m, which we'll treat as a constant, and now we're going to integrate this Maclaurin's bracket. Right, so it's Maclaurin's bracket to the power 1. So if I want to integrate something to the power 1, it's going to become to the power 2 divided by 2. So Maclaurin's left hand bracket x minus 2/3 L to the power 2, and we'll put the half in front. And again, what have I forgotten to do? Well, I should notice that we should be looking for C1 and C2 here. So I've forgotten to put these constant terms on when I do my integration. So for D1, that's going to be add on my first constant, which we call C1. When I integrate a term and it's got integrate a constant, it becomes C1 times x. And when we integrate that equation, we're going to have another constant, and we'll call that C2. So now everything's fine, and we've done A, B, C, D, E, all using Maclaurin's brackets. And we're almost, say, about 10 minutes into the question. Okay, so for part F, where we're looking for the terms, what we want to do here is we want to obviously find what these C1s and C2s can be. So these are my Maclaurin's bracket C1s and C2s, they're not the conventional ones. But what boundary conditions do you use for Maclaurin's brackets? Well, you've only need to do boundary conditions, makes things a bit easier. So you can have the boundary condition that y equals 0 when x equals 0, and that y equals 0 when x equals L. So they are going to be my two boundary conditions. Obviously the first boundary condition will be the simplest one to apply, so y equals 0, first term becomes 0. When we put x is 0 in here, that term inside the bracket becomes negative, which means it switches off, so it becomes 0 plus C1 times by 0 plus C2, and on the whole you'll tend to find that C2 should become 0 for most problems. So that's our first boundary condition. What about our second boundary condition? This one's a bit more tricky, and in this case we're going to be applying the fact that y equals 0 when x equals L. So we've got 0 on the left hand side, x equals L on the right hand side, so we've got x to the power 3 divided by L, so that becomes x squared. So overall I'm going to get minus m divided by 6 L squared. Okay, my next term. So let's put the x equals L inside the bracket. So we've got L, take away 2/3 L. Let's ignore the L's at the moment. Let's say talking numbers. So we've got 1, take away 2/3, and then we want to square that. So we've got a 9th coming inside here. So 9th, and we want to times that by a half for the term outside. So we've got an 18th. So overall, in terms of the numbers, we've got a plus 18th going on there. Now let's deal with the variables. We've got an m, and then inside the bracket we're going to have an L, which is going to be L squared, and that's it. That's done. Now C1 times by L, and our C2 is just 0, so well, let's not bother to write that around. So that we want to rearrange this equation. To rearrange it, to find what C1 is, we rearrange this. Let's use our calculator to do the work for us, because we're lazy. So when we take the minus 6 and bring it over to the left hand side, that becomes a plus 6, 1 6. Take the 18th, take it over to the left hand side, that becomes a minus 18th. And we're going to end up with a 9th over on the left hand side. So we're going to have a 9th times by ml squared, but notice we've got C1 times by L, so that ends up as a 9th ml when we divide through by the L. So we've got our coefficients, our C1 and our C2, but they're Maclaurin's coefficients, but they're not quite the same thing as the conventional coefficients. So if you wanted to, you could leave your solution like this. You'd probably get it all marked completely correct. If you want to get, certainly you'd probably get, I would guess, I don't know, about 7 out of 10. I certainly would be given that. I don't know if Anna will give you more, but if you want to be sure and get 10 out of 10, what you want to do is take your last equation, E, and then split it up into the two parts that you would get if you was doing it conventionally. So for the section from A to B, take your equation and say to yourself, what would happen if we've got a value of x less than 2/3? Well, in that case, your Maclaurin bracket term will get switched off and it becomes set to 0. So that will give us our first term here. So we'll get the minus x to the power 3 divided by 6l. Our next term, we switch it off. And the next term that we're going to get is going to be C1 times by x. So C1 is 1/9 ml, and I'm forgetting to times it by x, but don't worry, I remember later on. Okay, and now let's go for the next bit. I'll remember to multiply that by x in a minute. From BC. So what happens when we go from BC? Well, in this case, the Maclaurin's bracket will get switched on. So all I'm going to have to do is write out this equation again and change my triangles into nice curved brackets. So EIY equals minus x to the power 3 divided by 6l plus, so now the expression gets switched on because x is more than 2/3 L. Let's get rid of this term, so correct myself some space. So that's x, take away 2/3 L, close the bracket to the power 2, plus our C1 times by x. And our C1 is 1/9 ml, and I'm forgetting to times it by x. I will notice in a minute when I look at my final answer. So looking at my final answer, I can see that everything seems to be everything seems to be m x to the power 2, except for my last term. So where have I gone wrong? So I start looking at the answer above. Oh, and I notice that the x should be there. So let's put the x on the end. And then if you want, I think this is 10 out of 10. Although, strictly speaking, I haven't told you what C1 and C2 is explicitly for the section BC, although I have done for the section AB. Notice in this particular case for section AB, C1 is going to be the 9th ml and C2 equals 0. But for section BC, if I did want to find what C1 and C2 is, what I'd need to do is expand out this bracket. Now notice this isn't as painful as it sounds, because your C2 is what you're doing is now comparing and gathering like terms, and you're only going to get the constant term appearing inside the bracket. So when you multiply out that bracket there, you are going to have the minus 2/3 L. You're going to square it, multiply it by the 2 at the front, and that will be your C2. And then when you expand out that bracket again, your cross term, when you multiply the x times by the 2/3 L, that will be your the only term that's associated with your C1. Okay, so I'll leave it there.